Hey everyone, and welcome to this tutorial on quantum circuits with Qiskit. My name is Asbah. I am a Python developer focusing on machine learning and quantum computing. In this tutorial, I will walk you through step-by-step guide how to construct and run quantum circuits with Qiskit in Python. Qiskit is an open source software development kit for quantum computing. Initially was developed by IBM. It provides a high-level Python interface for constructing and running quantum circuits on a variety of backends, including quantum computing devices. Quantum circuits are a way of representing quantum programs. They are made up of a series of gates that separate on quantum registers. Quantum registers are also a collection of qubits, which are the basic units of information in quantum computing. In this tutorial, you will learn how to use Qiskit to construct and run simple quantum circuits. Don't forget to like, share, and subscribe, and also write comments in the comment section of this video. You'll also learn about some of the key concepts in quantum computing, such as superposition, entanglement, and measurement. If you are interested in learning more about quantum computing, I encourage you to watch this video. The topics that will be covered in this tutorial are construct multi-qubit quantum circuits, register with Qiskit, measure quantum circuits in classical register, use single and multi-qubit gates, use barrier operations, return the circuit depths, extend quantum circuits, and finally, I will show you how you can print the constructed quantum circuits in human-readable format using OpenQASM string. Before we get started, you need to install Qiskit on your Jupyter notebook if you are not installed yet. You can use pip install Qiskit. Then you can import the necessary classes from Qiskit module. Here, we are going to use quantum circuit class, quantum register class, and classical register class. So you need to import those classes from Qiskit module. Then the first step is construct a multi-qubit quantum register. You can use a quantum register class from Qiskit to construct a multi-qubit quantum register. To do this, you can use the quantum register class. Then you can pass two parameters into this class. The first one is the number of qubits, and then the name of the register, QR. These parameters are very important. Once you run this line of code, the quantum register named as QR with 2 qubits can be created. This register serves as a container for qubits in a quantum circuit and enabling the implementation of quantum operations and computations on the qubits within the circuit. So first of all, you need to create a quantum register with multiple qubits and the quantum registry name. The next step is measure quantum circuits in classical register. This can be done using the register class, classical register from Qiskit. This also can pass two parameters, the qubits that can be stored or measured as a result, and the name of the classical register, which is C. So a classical register with 2 qubits is created. This classical register is used to store and hold the measurement results obtained from the quantum circuit qubits. In this case, the classical register has 2 qubits, which means it can be stored the measurement results of 2 qubits. And C represents the name of the classical register, which can be used to identify the register within the context of quantum circuit. Once the classical register is created, it can be associated with the quantum circuit for measuring the qubits. Then finally, we can use the measure method that used to associate specific qubits with specific bits in the classical register, which allowing the measurement results of the qubits that to be stored in the classical bits for further analysis and processing. Now we go to the third step. Once we construct the multi-qubit registry and measure the quantum circuits in the classical register, we can create a quantum circuit. To create a circuit, you can call the quantum circuit class from Qiskit and pass 2 parameters to this function. The parameters are the quantum registry and classical registry. Now we are constructing the quantum circuit and the 2 qubits quantum registry and 2 qubits classical registry. In this case, the quantum circuit is being created. The quantum circuit function is used to create a new quantum circuit and provided with a quantum registry and classical registry as arguments. This quantum circuit will operate on the qubits from the quantum registry and store the measurement results in the classical registry. It serves as the canvas for applying quantum gates and executing quantum algorithms. Now, we can use single qubits and multi-qubit gates. To use a single qubits, we can use circuit.h and QR at index 0, which is H gate. And the other is the second qubit is at position or the second position, which is QR at index 1. This is also called Pauli's X gate. So the first one, circuit.h function, applies Hadamard gates to the qubits stored in the first index of quantum registry, QR. So the Hadamard gate is commonly used in quantum computing to create superposition, an essential concept in quantum algorithms. And the second one is, sorry, this is not X, Pauli X gate. This applies a Pauli X gate to the qubit stored in the second index of quantum registry. Because we have stored 2 qubits in the quantum registry, which is the first index in the quantum registry, that is Hamadar gate. And the second one is the Pauli X gate, which is stored in the second index of quantum registry. So this X gate The execute to the qubit stored in the second index of the quantum register. The Pauli execute is a fundamental single qubit gate that corresponding to essential bit flip and is often used for simple quantum manipulation and demonstration. So this is so-called single qubits. That is applies the superposition, which is an essential concept in quantum algorithm. Okay, now the next is use multi-qubit gates. This is a little bit different from the single qubit gates. In this case, we're going to use circuit.cx function, and we pass the qubit stored in the first index of quantum registry 0, and the qubit stored in the second index of quantum registry. So this is called C naught, controlled naught, C naught gate. So this applies a controlled naught gate to the qubits stored in the quantum registry at position 0 and position 1. The C naught gate is a fundamental 2-qubit gate in quantum computing that can perform an operation on a target qubit on the state of control qubit. So in this case, the qubit at index 0 is used as the control qubit, and the qubit at index 1 is called the target qubit, because it is multi-qubit gates. So that is called controlled NOT gate. So the application of the C naught gate can create entanglement. So this can create entanglement. But the first one was created superposition. The two concepts are very, very stressed and essential in quantum computing algorithm. Okay, then we can use barrier operations in quantum circuit. So to use a barrier operation, we can code circuit.barrier function. This method that inserts a barrier in the quantum circuit, it is a visual aid and does not affect the quantum computation itself, and also the barrier separates the operation before and after it, which helping to organize and visualize different stages of the quantum algorithm or circuit. Now we can call the method measure circuit.measures that measures the quantum circuit, which holds the quantum registry in the classical registry we have defined earlier. So we call quantum registry and the classical registry here. So this method in Qiskit actually the qubits in the quantum registry QR with the classical bits in the classical registry CR for measurements, because the classical registry holds the measurement results of quantum qubits in the quantum circuit. So this operation measures the qubits and stores the measurement results in the classical bits. So the measurement results represent the state of the qubits after the quantum computation, and they are crucial for retrieving classical information from the quantum computation. Now we can return the circuit's depth, the path of the circuit. So we can print circuit depth. Circuit dot depth function from Qiskit. So this returns integer representation that representing the depth of the quantum circuit, indicating the length of the critical path or the longest sequence of quantum operations in the circuit. So this is very essential. So this is the depth of the quantum circuit, which is 4 in this case. It may be 3, it may be 5. So it is not always constant. Okay. So which means this is the longest sequence of quantum operations in the circuit. That's very important. You can print out the circuit depth, look like this. Now we can also extend quantum circuit. Now we have constructed the quantum circuit, but we were used 2 qubits, and we can extend that quantum circuit using this method. Okay, let's apply this extension of quantum circuits. We can use quantum register method, and we pass the qubits that we want to extend. For example, in this case, I want to extend 1 qubit in the existing circuit. So the previous was QR. Now I can use different name. Okay, Q2. Let's say Q2, and this quantum registry is QR2. Previously was QR. Now I can add the registry into the circuit using add register method, and I can pass QR to that request circuit. Okay, now is added, and I can also use the single qubit gate, Hadamard gate or H gate. So I can use, I have only one registry, 1 qubit, so which is stored in the first position only. So I can use QR2 at index 0. All right, now I have constructed my own quantum computing circuit. I can now print out the circuits in human readable format using OpenQASM. Circuits.qsm. As you can see, this is the circuit I have constructed in this tutorial. So everything is readable. In the initial, I have constructed quantum registry with 2 qubits. Then this is quantum registry, the second extended quantum registry here, which has 1 qubit. I have also created a classical registry with 2 qubits. Then I used a single qubit gates. I also used multi-qubit gates, which is T-naught gate. T-naught gate. And I also used barrier measurement that measures the circuit result. And finally, this is a single qubit, which is extended in the existing circuit. So this is the circuits I have built in this tutorial. So you can practice using different qubits. You can use 3 qubits or 1 qubit or 4 qubits. So I hope you enjoyed in this tutorial and learned something new. If you have any questions, you can ask in the comment sections of this tutorial. Don't forget to subscribe to my channel for more tutorials on quantum computing and other artificial intelligence topics. Thanks again for watching.